Go.
Assalamu alaikum. I am Sadia Afroz. My role SK019033. My group name is GS10 Differentiable. Our topics data representations, the number systems. An introduction to binary number system. The binary number system is more like the decimal number system. In the decimal number system, we use the digits from 0 to 9, which gives the other name the base 10 number system. Whereas in the binary, the digits 0 and 1 are used only, suggesting the name the base 2 number system. Again, binary has by, which means 2 because we use 0 and 1 to build up this number system. Let's count. Since the binary number system is like the decimal number system, how do we count it? The decimal in decimal it's 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9 and so on. In binary it's 0, 1 and then. Well, it's like counting in decimals, but we reach 10 much faster. How to count? Well, how do we count in decimal? We start at 0, then count 1, 2, 3, 4, 5, 6, 7, 8, 9, and this is the last digit in the decimal. So we start back at 0 again, but add 1 on the left and we get our 10. The same pattern follows, and then when we run out of digits at 99, we start back at 0 again, but add 1 on the left, making it 100. We have done the same with binary. Binary is easy as 1, 10, 11, dot dot. How many binary digits are there? A binary digit is called a bit. As we have seen previously, 3 bits could be used to represent 8 possible numbers from 0 to 7. Would you find any more? In general, if n bits are grouped together to form a binary number, then they can represent 2 to the power n possible values. Thus, a group of 8 bits can represent 256 possible values. Similarly, a group of 16 bits can represent 65,536 possible values and so on. Now I am now my group members Asadul Islam will carry forward the presentation.
Thank you, Sadia Afroz. I am Asadul Islam. My role SA023. The minus thing. In a typical implementation, half of all possible values are reserved for negative numbers. The other half is used to represent 0 and the positive numbers. So a group of 8 bits can be used to represent from minus 128 to plus 127, including 0. We get to see the similar thing with higher number of bits such as 16, 32, and so on. The most common scheme for representing negative numbers in a computer's memory is the so-called twice complement representation. Binary to decimal. Let us consider the decimal number 345. 5 into 10 to the power 0 plus 4 into 10 to the power 1 plus 3 into 10 to the power 2, right? We can see each digit is odd, a power of 10 more than the digit to the right of it. In a similar manner, in binary, each digit will be odd, a power of 2 more than the digit to the right of it. So now we take the bit 110. 110 is 0 into 2 to the power 0 plus 1 into 2 to the power 1 plus 1 into 2 to the power 2 is equal to 10 in decimals. The addition. The rules of adding binary numbers. 0 plus 0 is equal to 0. 0 plus 1 is equal to 1. 1 plus 1 is equal to 10. Note that the other rules are same as the decimal system, such that we add from right to left, and any bit greater than 1 is carried over to the column on the left. Let's try adding. Let's try adding 1, 1, 1. Let's try adding 11 to 13. Binary for 11 is 1011, and for 13 is 1101. 1011 plus 1101 is equal to 1100. But how did we do this? How did we do this? First column 1 plus 1 is equal to 1 0. We keep 0 in first column and carry over 1 to second column. Second column 1 plus 0 plus 1 is equal to 1 plus 0 plus 1. 1 plus 1 is equal to 1 0. Once again we keep 0 in second column and carry over 1 to fourth column. Fourth column 0 plus 1 plus 1 carry over is equal to 1 0 plus 1 plus 1 is equal to 1 plus 1 is equal to 1 0. Keep 0 in fourth column and carry over 1 in eighth column. Eighth column is equal to 1 plus 1 plus 1 is equal to 1 plus 1 plus 1 is equal to 1 0 plus 1 is equal to 1 1. Keep 1 in eighth column and carry over 1 in 16th column. The sum is 1 1 0 0 0. Thank you. Now my group member Tanziha Bushra will carry forward with the representation.
Thank you, Asadul Islam. Hello, sir. My name is Tanziha Bushra and my roll number is SK 1921. I'll be carrying forward with what Asad has told. So how do we add the negative numbers? We use the 2's complement arithmetic. How does the arithmetic work? We first have to complement the negative numbers that are given. That is, we change all the zeros to 1 and then all the ones to zeros, and then we add 1 to each of the complemented numbers. The final is the complement number that we want, and we simply add them now. So here the leftmost bit is the sign bit. If that bit is 0, then the number is positive, and negative if it is 1. For better understanding, we will be using the 8-bit integers, so we will be adding zeros at the front. As we have seen in decimals, we can write 86 as 086 or 0086, but the number does not change. Similarly, in binary, we can add as many zeros as we want to the left. The number does not change. Let's check our understanding by adding these individual pairs 3, 4, 3 minus 4, and minus 3 minus 4. Well, when we add 3 plus 4, we know the result is 7. So adding zeros before 7 in binary, we get 11, and before 4, we get 100. So 11 plus 100 is 111 in binary. This was a simple addition. 7 in binary is 111, so we are correct. Let's check the next one out. 3 plus minus 4 is equals to minus 1. 3 is a positive number, so we don't change it. We don't complement it or change it. 3 remains as 11 in binary, and we change 4 to its complement number minus 4. When we add 1 to the complement number, we get the one we see here. So the addition is 1 1 1 1 1 1 and 1 1. The complement of this is 0. Adding 1 makes 1, so the result of this addition is minus 1. We carry the same thing out here, but we get an extra 9th bit. We ignore the 9th bit, and the complement of the result gives us 111, that is 7. So on addition, we get minus 7. Now I would like my group member Tithi Baroy to carry on forward with the presentation.
Thank you, Bushra. Hello, sir. I am Tithi Baroi. My role is SK019122. My topic is data representation. Why the tools complement arithmetic? Both positive and negative numbers can be added by the rules of ordinary addition. 2. The resulting answer would be correct, including the proper sign. 3. The design of computer circuits can be simplified. Computer work in the binary number system, while we are more comfortable to the decimal number system. Programmers can design a program so that the computer takes input in the decimal numbers and convert it into bit for processing and then show inputs in the decimal number again. Scientists and engineers face problems so as they work directly with the binary representation coded into the computer. In some cases, programmers face problems too. The problem. Individual bits or group of bits with a word might contain status information about the operation of some machine. If so, the programmer will have to consider the individual bit of the word and work it in binary number system. Scientists and engineers face problems directly because the binary numbers cannot easily managed and used when dealing with large bits. It is easy to get lost while dealing with such numbers. So what's the solution? The octal and hexadecimal numbers come to the rescue. The octal numbers. The octal, as the name suggests, contains 8 digits from 0 to 7, hence getting the second name of the base 8 number system. As we have seen before, a group of 3 bits can represent any numbers between 0 to 7. Thank you, sir. Now my group member Tausin will carry forward with the presentation.
Hello, sir. My name is Muhammad Tahsin Hassan, and I'll be carrying forward from the hexadecimal numbers. So basically, the hexadecimal or the base 16 number system contains 16 digits. The system uses 10 digits from 0 to 9 and 6 alphabets from A to F, such that 7 remains 7, but 13 becomes D in hexadecimals. A group of 4 bits can represent all numbers between 0 and 15 and 0 to F. So how do they work? Considering the binary number 1000001010001, for octal representation, we divide into a group of 3 bits and replace by the appropriate octal number. 100, 100, 001, 010, 001 gives 4121 in base 8.
Octal number শেষ করছো for hexadecimal representation.
Okay, for hexadecimal representation, we divide into a group of 4 bits and then replace by the appropriate hexadecimal number. For example, 100 represents 1, 0101 represents 5, and 0001 represents 1, gives 851 in base 16. So why base 8 or why base 16? It represents the same pattern of bits as the binary number, but it is more compact. Much easier representations are more handy to use. The good news, Fortran programming language can input or output numbers in any of the 4 formats of hexadecimal, binary, octal, or hexadecimal. That is all from us. Thank you, sir.